Good evening, everyone. Welcome back. Going to start you off on Wednesday by walking you through exercise 3 from the problems for the week. Now, in both parts A and part B, we have the same rod, but with two different forces applied to it. In both cases, you're asked to calculate the torque on the rod due to the force. Torque, which we calculate from R cross F, where F is the force applied, and R is the displacement vector pointing from the axis of rotation to the point on the body where the force is applied. Now, there are a few different ways you can actually calculate out this cross product, so I'll demonstrate one of each for you. In part A, we'll first calculate the magnitude of the torque. The magnitude of your cross product will be the magnitude of the first vector, r, times the magnitude of your second vector, the f, times the absolute value of the sine of the angle between your two vectors. In our case, our r vector points from the pivot in the middle to the left end where the force is applied. So we have a magnitude of half the length of the rod, 0.7 meters. We multiply that by the magnitude of our force, 35 newtons. And then we multiply by the absolute value of the sine of the angle between the two vectors. Now, this is a little bit tricky here, so we need to look at our diagram closely. Our r vector points from the pivot to the left. So if we extend it, we see the angle is going to measure from 9 o'clock down and around to our force vector. We have 90 degrees from 9 o'clock to 6 o'clock, and then another 30 degrees from 6 o'clock to the force vector. So the angle is 120 degrees. The reason I put this in absolute value is I don't want to worry about the positive or negative signs. I'm going to assign that when I figure out my direction. So I wanted to keep the magnitude of my vector positive. And plugging the numbers into our calculator, we get a magnitude of 21.2 Newton meters for our torque. Now that we've got the magnitude, we assign the direction using the right-hand rule. I should put my coordinate axis on here for one thing. I'll call my to the right x, up y, and that means my positive z comes out of the page. Remember, a vector coming out of the page we denote as a circle with a dot in the center of it. So positive z comes out. Now, to find the direction of torque for the cross product, I point my fingers along the r vector to the left, to 9 o'clock. Then I curl my fingers in the direction of the second vector of the product, in the direction of f. So I curl my fingers down to the right, and then the direction of my thumb tells me the direction of my torque. Since my thumb is pointing out at me, out of the page, I say that my torque is in the positive z direction. So our finished torque vector is 21.2 Newton meters in the z-hat direction. That's our torque for part A. So what we did here was we first calculated the magnitude of the torque using the magnitude of r times the magnitude of f times the absolute value of the sine of the angle between our vectors. And once we have the magnitude, we assign the direction using the right-hand rule. Point our fingers along r, curl along f, and then our thumb points in the direction of the torque tau. For part B, we're going to try this another way. We'll just go straight to the torque vector by writing out our r and f in unit vector notation. Our torque is again r cross f. We're just going to work that out in a slightly different fashion this way. Our r vector points from the pivot to the right end of the rod. So it's got a length of 0.7 meters, and it points in the positive x direction. To the right, that's my positive x. So I can express my r vector as 0.7 meters x hat. Now I'm going to do a cross product of my r with my f vector. My f vector has a magnitude 35 newtons, but I want to break it down into unit vector notation. So I'll have 35 newtons times cosine of 30 degrees for my x component, cosine of 30 because I want to pick out the near side, the adjacent angle of my forced triangle, and the y component will be 35 newtons times the sine of 30 degrees, because I want the opposite leg of my triangle. All right, so now I start distributing things for my cross product. I can distribute out the 35. So I've got 35 newtons times the 0.7 meters gets me a 24.5 Newton meters out front. And now I distribute my x hat from the r vector across the cross product. So for my first term, I'll have cosine 30 degrees, x hat cross x hat. And for my second term, I'll have sine of 30 degrees, x hat cross y hat. I distributed the 35 newtons part out front, so that's all the way to the left. And then I do the cross product of x hat on each of my terms. So my first term with the cosine 30 degrees is x hat cross x hat. My second term with the sine of 30 degrees is x hat cross y hat. Now x hat cross x hat is 0 because it's a vector crossed with itself. Every vector is going to be parallel to itself. So a vector crossed with itself will give us 0. And x hat cross y hat will give us positive z hat. We can see this from the right-hand rule. If we point our fingers along x hat, curl to y hat, our right hand will give us a positive z hat out. So the cross product has killed off my first term and left us all together with 24.5 Newton meters times sine of 30 degrees in the z hat, positive z hat direction. Or simplifying this a little bit further, we get 12.3 Newton meters in the positive z hat direction for our torque. Now we've got two ways to evaluate our r cross f, get the torque vector out of it. Good luck with the problems. I'll be available if you need any help.